Okay, in this video we are going to talk about pressure forces on a fluid and how they are different from shear forces, and we'll talk also about how shear force in a fluid is set up and how it can be calculated. So you've already done deformable body mechanics, and so we know that when you take a beam and subject it to axial loading, there's at any section here, there's going to be some kind of stress. So if I took the normal force in this direction, so in my cut section, if I draw the cut section alone here, there's a normal force acting on that surface that's perpendicular to the surface. We call that a normal stress. And if there had been a tangential force acting on that surface, that would be called a shear stress. So the shear stress refers to the force along the surface rather than perpendicular to it. And the pressure in a fluid is essentially the normal stress, so it's normal to the surface. More generally, in a fluid, because we don't have these rigid surfaces that we can take slices of, we would probably define that by taking some arbitrary surface in a fluid and saying, well, if I took my normal to that arbitrary surface and a tangential, my resultant might be in some other direction. So that's my actual force on the surface. F sub n would be normal and F sub t would be tangential. So what we do is define pressure as the force normal to arbitrary surface in the fluid, and shear is the force parallel to the surface. Why is this important? We defined a fluid as a material that cannot resist shear force. And that's why we had this example earlier of looking at two parallel plates where the fluid is being pulled along itself, right? So parallel to the surface is where this force is acting, and that's the direction in which a fluid cannot resist any forces. So let's define stresses and strains in a liquid or a gas, a fluid essentially, and compare how that works when given what we already know about strains and stresses in a solid. So if you took a solid and we go back to that same geometry that we talked about earlier, where there's a solid between two parallel planes and we are applying a force F in the tangential direction, so that force should create a shear stress. And if I looked at some plane in this direction, that would presumably deform by some small angle given by delta beta. So I'm going to call that delta beta. And at this top plane, that's going to result in a deformation delta A. So that's my original plane here that's moved over there as a result of this external force applied. So one way to define the strain here is just the angle of deformation. So I could call my strain as delta beta which for small beta or small delta beta would be the same as tan of delta beta for small delta beta. And tan of delta beta is something that I can calculate if I assume that my spacing here is given by b. I can say that my delta beta, which is now tan delta beta, is approximately equal to delta A over b. And so this is my strain. This is my strain. Now, if I want to define the pressure acting on this plane, the pressure is given by the force per unit area. That's the definition of pressure. And so the force per unit area in this case would be F over B times 1, where 1 is the unit length perpendicular to the plane. So one measure of deformability, which for the solid is typically a Young's modulus. But more generally, what we want to say is we want to quantify how that solid or the material really responds to an applied stress. So this is my applied force, which translates to an applied pressure, and I want to relate that to the resultant strain, which in this case is the angular deformation. So the measure of deformability would be pressure over strain or stress over strain, which would be P over delta A over B. For a solid, this would be a Young's modulus. For a fluid, we define this as a viscosity, and we'll do a more precise definition in the next video.